My name is Patty Ford, and I want to thank you for joining me today for the Toshiba Communications Basics. This is Session A. This course is designed to provide a high-level overview of basic communications theories and concepts. We're doing this course in preparation for the Toshiba product and technology courses. It's designed for sales reps that are new to the telecommunications industry. There are many online tutorials on the internet for sales reps that want additional information in communication history and theory, local and long-distance practices, regulatory issues, and technologies. Upon completion of this course, you will be able to define analog and digital communications, list types of access from the public switch telephone network or PSTN, explain proprietary versus standard devices, and use basic communications knowledge to attend Toshiba product classes to sell our communication systems. This course is done in 3 sessions. Session A covers communication theory. We'll talk about analog and digital communications, circuit switched versus packet switched communications, and standard versus proprietary systems, as well as session initiation protocol and proprietary IP options. The next section is the players and access options, and the third session, Session C, covers systems basics. This module is about the basic premise on which today's communications methods were founded. It contains background information to help you understand network methodologies and differences that are used in networks that Toshiba equipment interconnects. Let's begin with the original method used in traditional telephone service, analog communications. Analog means copy, and in this case we're talking about an electronic copy of sound waves. If you could picture a sound wave, it's sometimes described like the ripples you would see if you dropped a pebble into a pond of still water, ripples of concentric circles moving in an outward progression. An analog sound is an electronic copy of an original sound or a signal as found in nature. For instance, an analog audio signal follows the same pattern as the vibration and air pressure caused by the original sound, or a copy of the vibration that your eardrum hears as the waves of pressure hit it. Speech coders turn audible sounds into electronic analogs of those sounds. The waves which are described in these systems are called sine waves. Let's briefly look at how analog transmission works. Telephone transmitters change sound waves, or our voice, to analog signals. Sounds are translated into various forms of amplitude and frequency for tone, pitch, volume, etc. Amplitude is the height of the signal. Frequency is the number of recurring signal pulses in a given time. Telephone receivers on the opposite end converts the analog wave to sound waves. The analog voice frequency equals 4,000 Hz. However, the telephone and modems only use about 3,000 Hz, and the remainder is called guard band. Analog systems use dual-tone multi-frequency, or DTMF, to communicate. DTMF is used by the typical touch-tone or analog telephones in our homes and many other computer systems. DTMF assigns a specific frequency consisting of 2 separate tones to each key so that it can be easily identified by a microprocessor. Many office systems also use DTMF to communicate between systems and voicemail. DTMF additionally is used for integrated applications like checking a bank balance or reordering a prescription by telephone. Through ongoing development and technological advances, we've found several limitations with transmitting analog signals. Over distance, analog signals fade due to weakened signal amplitude. Amplifiers are built into networks to strengthen these signals. However, amplifiers also strengthen any extraneous noise. Technologists have come up with another way to represent sound, through digital communications. Digital is a different kind of representation of a signal. It does not attempt to copy the original signal, but instead it represents it with numbers or digits. Digital describes electronic technology that generates, stores, and processes data in terms of 2 states, positive and non-positive. Positive is expressed or represented by the number 1, and a non-positive by the number 0. Thus, data transmitted or stored with digital technology is expressed as a string of ones and zeros. Each of these stated digits is referred to as a bit. By representing sound through digital signals, you have electronic pulses digitized to represent ones and zeros, this allowing transmission that provides both higher speeds and higher accuracy. Pulse code modulation, or PCM, is the digitization technique used to convert analog to digital transmission for traditional telephone networks. PCM samples the analog wave 8,000 times per second. Each sample is quantized at the place where it falls at a different point on the wave. Each sample point is assigned or encoded an 8-bit value of ones and zeros. So we have 8,000 samples per second multiplied by 8 bits, which equals 64,000 bits or 64 kbps. This is referred to as digital signal level 0 or DS0. The PCM technique is accomplished by an analog to digital and digital to analog converter called a coder-decoder or a codec. With digital signals, pulses also fade over distance. However, digital regenerators build the bit stream perfectly rather than just boost the volume. This makes them less subject to noise because there is no bit position for extraneous noise or a way for the mathematical formula to pick up extra noise or interference. This makes digital signals somewhere between 20 to 100 times clearer than analog signals. Now that we've discovered analog and digital technologies, let's spend a few minutes examining how these technologies work on different kinds of networks. We'll first talk about the traditional telephone network process, circuit switching, and then compare and contrast it to packet switching, which was originally developed for data transmission. Traditional telephone or voice networks are circuit switch networks. These networks are also referred to as TDM, that stands for time division multiplexing. These networks were designed for a single provider, like the local exchange carrier, to carry short-duration single applications, like a voice call. We refer to these networks as the Public Switch Network, or PSTN. They're considered connection-oriented. The connection is dial, ring, answer, and all of the signaling that those functions require. This is established before transmission occurs. Connection-oriented protocols determine, first of all, how the connections are created and supervised, that security is checked and quality of service is verified, and then only after those signaling processes are completed is the information or the call transferred, and when complete, the connection is released. On a traditional circuit switched call, the call has complete use of the circuitry over which it passes. Circuit switch calls are typically any-to-any applications, like a voice call, a data via modem, fax, etc. Circuit switch calls are usage-sensitive billing, usually by the minute or by a volume call plan. Call setup time is also required. The overhead and the setup signaling runs ahead of the call and on a different network. The way telephones and or telephone systems are connected to the PSTN or Public Switch Telephone Network in a traditional network is via the local loop. There are a variety of facilities that can make this connection. The different connection types between your home or office and the LEC, local exchange carrier, offer different benefits. We'll talk more about the variety of local loop connections in the next session. In this picture, you see distribution channels connecting to subscriber to feeder. Subscriber loops can be analog or digital. Feeder migration may begin analog and be converted to digital in the path along the way to the local exchange carrier central office. Let's cover the steps in circuit switch calling process using an analog or home phone for the example. The caller lifts the handset and sends loop start signal. Some businesses may use ground start if required by the customer premise equipment or CPE. The central office detects the loop start signaling, and then the CO provides the dial tone. The CO collects the DTMF or pulses, and the call is routed by a network switching matrix and time slot interchanges. It's a port-to-port connection established through the signaling to the call party, and the calling party gets ring back and then an answer signal. And then the conversation is assigned to a dedicated time slot through the length of the call, giving it exclusive use of that circuitry. When the call is completed, they get a disconnect signal and detection. Only when the conversation is ended does that time slot in the network circuitry become available for another call. Packet switching refers to the set of protocols that define the way digital messages are divided into packets before they're sent. Each packet is then transmitted individually and can even follow different routes to its destination. Once all the packets forming a message arrive at their destination, they're recompiled into the original message. Local area networks, or LANs, and wide area networks, or WANs, have protocols like TCP/IP that are based on packet switching technologies. Packet switching techniques were developed originally for data or for sending information that was delay tolerant. A network is a group of two or more computer systems linked together. There are many different types of networks, including local area networks or LANs. The computers are geographically close together, that's usually in the same building. Wide area networks are WANs. This is when computers are farther apart and are connected by telephone lines or radio waves. Like two LANs make a WAN, for example. There's also campus area networks or CANs. These computers are within a limited geographic area, such as a campus or a military base. We also have metropolitan area networks or MANs. A data network is designed for a city or a town, and then there's the home area network, a HAN. This is a network that's contained within a user's home that connects their personal digital devices. This is a very high-level look at a packet switching operation. Messages are broken into small pieces called packets. Packets contain data, sender identification, packet sequencing, and address information. Multiple users' packets are interspersed efficiently and transmitted to the next node or switch on the packet switch network. Different packets from the same message may travel by different routes through the network. As packets reach the receiving end or final node, they sort and assemble the message for delivery. This is accomplished in a few milliseconds. Delays are minimal, usually less than a second. Packet switching allows many users to access data communication benefits without the expense of a dedicated network. The messages crossing these facilities share the facility. There's no exclusivity per contact like on the public switch telephone network. There are a number of protocols or rules of engagement for these types of networks to communicate. TCP/IP, originated for the Internet, is one that's most commonly used today. The TCP/IP protocol suite established the foundation for the Internet. However, now most protocols in the suite are developed by the Internet Engineering Task Force, or the IETF. The suite of TCP/IP protocol core functions are addressing and routing in the network layer and transportation control in the transport layer. IP, Internet Protocol, addresses the network components by assigning a unique number to each device. We call this an IP address. TCP, Transmission Control Protocol, provides the stream data transfer, transportation reliability, efficient flow control, full duplex operation, and multiplexing. Voice and data consolidation is the transmission of both voice and data over a single packetized communication network. It combines the circuit switch voice network with the routed packet data network to achieve efficiencies in technology and reduce equipment cost. To achieve consolidation, data networks must be more reliable with a higher quality of service to be suitable for delay-sensitive applications, such as voice. QoS, or quality of service, is a networking term that specifies a guaranteed throughput level and in turn guarantees a quality voice conversation with which our customers will be satisfied. Voice over IP uses the Internet Protocol to transmit voice as packets over an IP network using our VoIP protocols. Voice communications can be achieved on any IP network regardless of whether it's the Internet, intranet, LANs, WANs, etc. In a voice over IP-enabled network, the voice signal is digitized, compressed, and converted to IP packets and then transmitted over the network. VoIP or VoIP signaling protocols are used to set up and tear down calls, carry information required to locate users, and negotiate capabilities. To recap, let's compare and contrast circuit switching and packet switching. To contrast, traditional telephone service has historically been based on circuit switch technology, in which a dedicated line is allocated for transmission between two parties. Circuit switching is ideal when data must be transmitted quickly and arrive in the same order in which it's sent. This is the case with most real-time data, such as live audio and video. Packet switching is more efficient and robust, originally designed for data that can withstand some delays in transmission, such as email messages and web pages. Packet switching is now enhanced to be used for voice and video applications along with traditional data. Thank you for attending Session A of the Toshiba Communications Basics course. There are 2 additional sessions for this course.